My great pleasure to introduce Manfred Warmuth. Professor Warmuth is full professor of computer science at University of California in Santa Cruz. He received his PhD from the University of Colorado at Boulder in 1981. He's been at Santa Cruz for most of his life. He is very well known for a number of areas, including online learning and boosting. Some of you may not know this, but Manfred is also a very avid beekeeper. He keeps chickens, rabbits, all kinds of things. Over the last 8 or 9 years that I've known Manfred, he has taught me a number of things. And today he's going to teach us about optimization view of boosting. Thank you very much.
Okay, my name is Manfred Warmuth, so ask questions. I'll talk about a totally different area, maybe that you have heard, and you know, if you don't understand it, just raise your hand, why? Okay? So hopefully you have fun. So I'll talk about boosting. A lot of this work was done with Vichy, and I'll give some basic introduction this morning. That's introduction to boosting. And then I talk about the big picture of developing machine learning algorithm, what kind of regularization, squared Euclidean distance versus relative entry regularization. This leads to additive updates, this leads to multiplicative updates. And I'll develop my slides online. I'm in online learning. So depending on how it's going between us, I'll add more or less stuff, you know. We'll see. Okay. So first of all, boosting addresses a classification problem. You start out with a fixed set of labels examples. Examples might be text, labeled spam, non-spam. For simplicity, plus minus 1 labeled. Okay, we can handle slightly more general labels, but classification example, that's the easiest case. Now, very often in machine learning, what happens is it's very easy to get simple rules of thumbs that classify slightly better than 50%. Well, 50% is easy, right? You just get a hypothesis that's random. Right? 50% is easy. So you want to do slightly better than 50%. Right? So error is 50%, a half minus epsilon. Right? A little bit better. Okay. So we call those weak learners. Okay. So then Michael Kearns asked in his thesis, the student of Leslie Valiance, who just got the Turing Award. Actually, machine learning is getting pretty popular these days. You're in the hot field. It becomes sort of the structural science of all of computer science. Everybody wants suddenly machine learners. I don't even have time to talk to all these people. Okay, so he asked the question in his thesis, if you have weak learners, can you then boost these weak learners to be strong learners, so arbitrarily accurate? So if you have one, you always can provide one that's 49% accurate. Can you use that can you boost this to an accuracy of 1%, let's say? You understand the question? So that's what the term boosting means. Boosting the weak advantage over the random classification to be strong advantage. Okay? So from a half minus epsilon down to some very small number. Now, the first boosting algorithm was done by Rob Shapiro in his thesis. Okay, he was just across the street at MIT. And then Freund and Shapiro, Freund was one of my students, they have a boosting algorithm that's 5 lines of code. You know, very often in machine learning, the algorithms are totally trivial, but the analysis is complicated. So this is a classical example of that, AdaBoost. I'll talk about that algorithm. And then also I talk about fancier boosting algorithms here and where boosting comes from and so forth. But we assume we have a black box setup. We assume that somebody, we have an oracle, this is sort of from theoretical computer science, we have an oracle that provides you with weak learners for weighted examples. You have a bunch of examples, you have weights on them, and then your oracle always gives you a new hypothesis that's slightly better than 50%. That's what you assume. Okay? And then the boosting algorithm aggregates these many weak things and makes something bigger. So it's kind of from that area of many stupid things together get the things right. So if you, supposedly, I haven't done this experiment. It's always a good idea to have a big group. You just take a bag of coins, you drop them on the ground, and then you ask everybody how many coins there are, and supposedly the average gets it fairly accurate. So even you could do it. Okay, so this is combining many stupid things to something better. That's the idea, aggregation. And this is classical machine learning in the sense that you really don't do anything, really. You just combine things, right? That kind of thing. OK, so here's the protocol for boosting. The protocol is you maintain a distribution on a fixed set, let's say, of capital N binary labeled examples. OK? And then you have an iterative process. Right? You have an iterative process. Purdue goes on trial-by-trial basis. And in each trial, your oracle gives you a weak hypothesis or a base hypothesis. And then you update your distribution. Okay, you have a distribution on the examples. Well, this will become obvious because I have pictures. You have a distribution on the examples, and then then the oracle gives you a weak hypothesis, you update your distribution. And at the end, you output a convex combination of all the weak hypotheses you got. So that's the overall setup. You aggregate them. So the goal is that the final hypothesis is highly accurate. And of course, you want a small number of iterations, right? And you don't want overfit. Now, of course, if you build weak hypotheses by just memorizing your data, you just take a random coin, and then you look at the labels and randomly flip, and flip a bunch of labels so you have a little bit more than 50%, that's going to overfit. If you put junk in, you get junk out. But if your hypothesis, your base hypotheses are somewhat simple, in machine learning, they use something called the Vapnik-Javanenkis dimension, some combinatorial complexity. If it's small complexity, then you will have no overfitting, and this thing will learn. OK? Good. So example, you might want to classify spam. You have a bunch of emails, right? So what's the rules of thumb? Well, it has Viagra in the text, and it's mostly going to be probably spam. OK? It might be mailed from certain sites that are known to produce spam. Right? So that could be a rule of thumb. Do you understand? I'm giving you rules of thumb. Now, also, you want to be really a computer scientist. You want to steal from everybody else. You know? It's like that's what Microsoft did. At some point, they stole the spam filter from Google, and they probably did it vice versa. Right? And we in academics, we always steal from other smart people. But we reference them sometimes. So you want to steal any kind of thing you can get from anybody and put that, give that, and the oracle does it for you. It steals from everybody else. And those become your weak learner, right? So they don't actually have to be weak. If they're good, then that immediately will help you a lot if you have a good machine boosting algorithms. So it's basically the philosophy is you combine anything to get an improvement. Of course, if you do it too long and too much, and you have too complex hypotheses, or you have base hypotheses that are already overfit, you're going to keep on overfitting. So that's, of course, the main issue in machine learning. It's always good to take a large variety of different base learners, simple decision trees, support vector machines, nearest neighbors, from different families of algorithms as your base learners. I will talk about families in a moment. Questions so far? Okay, I'm doing all right then. No. Okay. So other problems, you might want to classify pictures as to whether they contain a dog, or does the picture contain a human face? Okay. In the most common setup, what happens is you already know your domain, right? You have some kind of a CompBio application, and you already know, what particular genes look like. You have certain patterns that you look for. So you have already a bunch of features that are suitable for your problem. You know them because you have worked with this problem for a very long time. And they're typically called features. And then your weak learner would just be a single feature that you have played with before. And then you want to have a small number of features and a linear combination of the small number of features that get you a good result. You understand? So your features become your weak learners. Often the features are real values. Now, since we have a classification problem, if you have real valued features, you turn these features into decision stumps. Very simple things. So if this is the ith feature and this is a threshold, then the decision stump hi theta would be feature I is bigger than theta. So if you have a bunch of real valued features, you can turn them into decision stumps. And to some extent, this is the most common kind of weak learner that is used in practice in many applications, decision stumps. So what is boosting? It's a simple, versatile technique for building strong learners from weak learners, provided that you have an oracle that gives you good base hypotheses. What good means, I will talk about pretty soon. They have to have some property. Essentially, they have to have low error or high accuracy. Okay? You can view boosting, and I know Dale Schurman talked about this, as coordinate descent. You have your huge feature space that is given to you ahead of time. Those are all your possible weak learners. Might be exponentially big. And then the oracle picks you greedily the next good feature, adds it into your ensemble that you aggregate, and then at the end you do a convex combination of, you output a convex combination of the small features that were selected by the oracle. So then you pick one coordinate in feature space at a time, right? And this is sometimes called coordinate descent. And the choice of your feature is greedy, because you pick somehow a good feature according to some measure of goodness. So it's a greedy feature selection thing, if you view it that way. Okay? Questions? So that's very basic setup of boosting. So this is going to be our running example. We're going to classify apples. Right? So these are the natural apples, and these are the artificial apples. We want to classify them. So there's two features. They're real valued features. This is redness, and this is lightness. I got these pictures from Gunnar Raj. I worked with him a lot on boosting. Everybody understand? So these are real valued features. OK. Good. So we have, let me first talk about classification setup. So the Artificial apples are, we want to select those for some reason because we're computer scientists. So these are the +1 labeled ones. And the natural ones, they rot. So we have -1. So we want to get an accurate classification. And we have 2 real features. Okay? So now, so these are real valued features. Now I want to use decision stumps. I want to get that across to you that decision stumps are usually the way to go. So here's an abstraction of it. I'll explain to you what the decision stumps do in a moment. Now, clearly, I could just draw a plane here, right? But for teaching purposes, I'm going to not allow that. I'm going to give you just weak learners. This would be a strong learner. It immediately does the job. Draw a plane and get perfect classification. So I don't want to get that. I want to get the teaching moment and handicap my learner and have only weak learners. And what do I do for weak learners? Something like this. That's a decision stump. It picked the first feature, put the threshold at 0.57. Bigger than that, classified as 1. Blue is 1. Otherwise, it's -1. So that's a decision stump. Right? And now I allow you all possible decision stumps. So your weak learner or your oracle picks thresholds along this dimension and threshold along this dimension. Yeah? So that's what it's going to do. And it always picks one that is somehow good. And I will be clear in a moment what it is. And then at the end, we're going to combine these threshold functions. And hopefully, we will separate this thing. Clear? So our binary features are stumps along these 2 features. Of course, usually you would have gazillions of different things. You just throw in all kinds of things. So, but this is our toy example here. So apples, abstracted it. And so now you see that because we have these weak learners, no particular decision stump can separate your data. There is no stump, if you walk along here, that perfectly classifies things. They can only weakly classify. They can get close to 50%. As a matter of fact, yeah, I'll show you the errors in a moment. So one can't do it. So our hope is to find a convex combination of the stumps along this thing and along this dimension. And the convex combination, again, will sort of do a step function type thing and separate the data. Right? So we aggregate the weak learners to do the classification. So here, what's the error? Well, we had 11 apples. This one is wrong. Do you see that? It's on the wrong side of the plane. It's red, labeled -1, but it's on the +1 side of our decision stump. Yeah? So it's 1 is wrong. So the error is 1 in 11. Now, we're going to switch to another notion that measures the quality. And there's a certain reason for doing it, because things become simple dot products. It's called the edge. Instead of working with the error, we work with the edge. What's the edge? OK, so here's the little picture. OK, here we have error. Error 50% corresponds to edge 0. Totally perfect, error totally wrong corresponds to edge -1. Totally right corresponds to edge +1. This thing is sharp. It's OK. So again, error 50% corresponds to edge 0. I have to pump this. And error, so random corresponds to 50%. Accurate corresponds to edge +1, and inaccurate to edge -1. technically what it is, it's 1 minus twice the error. Right? Okay. So I'll make this obvious in another slide. So perfect means +1. Wrong means -1, misclassified. Neutral, you know, sometimes these, the prediction. So what we're going to do is we're going to take the label and we multiply it by our weak hypothesis. And that's going to be our U. And this U measures the accuracy. And the edge is the weighted accuracy. Okay, so UN is the accuracy of the hypothesis, the current hypothesis, on the example, nth example. And edge is the average accuracy on all examples. Remember, we have a distribution on the example. It's very important. The distribution idea was key. Okay, so again, here we had our original apples. The left one is the labels. You see the labels +1 and -1. And then the stump classifies a certain way. And then the multiplication of both, that's your accuracy. So if the guys agree, then -1 times -1 is +1. Then you're accurate. Or if you're also accurate if both are 1, 1. So you see? But you're inaccurate if the two disagree. The product is -1. Huh? Maybe you fixed it. No. OK, so what happens is I'm going to look at the – did I show that already? No. So the size of my point that I draw corresponds to the weight. So what happens is after the update, you increase the weights of the misclassified ones. So remember, this was a misclassified one. That one, that guy's weight, fatness, is brought up. The distribution puts more weight on it after the update. This is what boosting does. It reweighs things to put more weight on the misclassified one, on the hard examples. So before that, they were all the same size because we had a uniform distribution. At the beginning, we didn't know anything. Then we had this classified. This guy was classified wrong. Oh, now this guy is brought up. Its weight is brought up, and everybody's weight is brought of the other guy goes down. Guys goes down uniformly because they all classified correctly, so that the total weight sums to 1. Okay, now the edge of the hypothesis, this particular weak hypothesis that we added, goes down after the update. Why? I'm going to put more weights on these guys that were misclassified, whose U values, whose accuracies were negative, were -1. So what happens is the edge of this hypothesis that you have after the update, after the reweighing, goes down. So that's sort of the philosophy. You add a weak learner, you reweigh them so that the edge of your current hypothesis and all the past hypotheses goes down. And then you find that the weak learner has to provide you with a new weak learner that has high edge again. So all the ones you have, you push the edges down, and the oracle is supposed to give you one with high edge. OK, so this is what it looks like before the second iteration. The oracle is always provided with a weighted combination of the examples. Again, the weights are the size of the points. Right? So after the first iteration, this one is fat. Now, the new weak learner that I pick most likely will get that one right. So the new weak learner is this. Right? So we pick, again, the oracle provides you with a hypothesis amongst all possible decision stumps, right? Bam, bam, bam this way, bam, bam, bam this way, with a high weighted edge, where weighted means according to the distribution. So it now got this right. It got one wrong, but this one was weighted down a little bit, so it actually has a lower edge. And now, after the second iteration, that guy's brought up because it was misclassified. You see that? It was misclassified. Chose the second hypothesis, reweigh after the second update. That misclassified example is now brought up. This one is brought up, as you see. Okay? So that's that idea. Now, pick another weak learner according to the weighted combination, right? This is what's chosen next. Now you will see the wrong one is this one. That one is going to get fatter now. You see? So here, before, afterwards, it's brought up. Now you pick another weak learner. Now you will see that this guy is wrong. You see, that guy is going to go up a little bit. You see that? And then you output a weighted combination. See? So the weighted combination is the following. Blueness means correctly classified. So everybody in here would be blue, and all the other ones are red. So it classifies all the examples correctly with a funny weighted combination of the hypotheses, which looks messy, but it does the job. So it aggregates those decision stumps along this and this dimension into a step function that classifies things correctly. Yes?
So when you increase the weight of one of the examples, how do you decide how to adjust the weight of the rest of the examples? Do you just do it uniformly?
What happens is you're going to see an example in a moment of the AdaBoost algorithm. It multiplies all the weights of the, you have already a distribution. Now each probability is multiplied by a factor, and then you renormalize. And the factor is going to be large if it was classified wrongly, and small if it was classified correctly. Yeah? So it's a multiplicative update. And then the next hour, I will talk about multiplicative versus additive updates. Where do they come from, big picture. Okay? But we will bring this out. Yes?
So do these different shades of red color, they indicate something different?
Yes. So this means the total, you do a weighted combination. And in this area, your thing was blue. So you did classify as +1 because you're going to threshold. And here you classify as -1, but you see that everybody, all the red ones are in the red shaded, all the red points are in the red shaded area, and the blue ones are in the blue shaded area, so you perfectly classify, even though there's no particular stump that can do it. But the aggregate can do it. So that's what's supposed to be the point.
But the shading also indicates...
Yes. How much? It's the certainty. If you compute the value here, it might be I don't know what it is, 0.3. The weighted combination in this area is 0.3. Because it takes the weighted combination of all of these, which are plus or minus 1, and it comes out to be 0.3. Do you see? So when it's positive, which would be this area, my thing is funny, okay? Then you classify as +1. Yes? Go ahead.
How are the weights decided?
Yes, yes. That's the boost. That's the meat of the thing. We're going to go slow. It's always good to ask questions beforehand, because then you have a notion of surprise, and then you learn. So that's the key trick. I formalize that in a moment. OK. So again, the boosting protocol. You maintain a distribution on the n examples. And then in each iteration, you receive a weak learner from the oracle of high edge. You now know what edge is. And then you update your distribution. You put more weights on the hard examples, the one that was misclassified. And then at the end, you output a convex combination. And notice there's two sets of weights. This is what makes boosting confusing but interesting. There's a weight on the examples and a weight on the hypotheses. And they are going to be dual to each other. Duality. Convex optimization duality. Linear programming duality. Game theoretic. Two players playing against each other. I'll bring all of this out. Totally cool. So again, this was our data representation. We had the weak classifier. We producted in the labels. This would be perfect. This is sort of the accuracy. The U's are the accuracy, the local accuracies. You have a bunch of labels, hypotheses, and then you compute the U's. And then the weighted accuracy was the edge. So now here's the simple AdaBoost update. So it's such a simple algorithm, you can memorize it. Okay, so here's the update. You use that protocol, and then here, how do you update the thing? Okay, you take the new distribution is the old distribution. This is the distribution before the trial, and this is the distribution after you do your update, right? So you take the new is the old times this factor. And the factor is e to the minus a weight times the accuracy, the local accuracy. So I'll talk about this. You have to understand every element of this. So twiddle means here it's proportional, so you always renormalize it, right? It's just a shorthand. Okay. Now, the accuracy in this in the exponent, well, if you would want to give the high accurate things more weight, then you wouldn't have a minus sign here. But if you want to give the inaccurates more weights, the factor is supposed to be high. You have a minus sign here. So you give the ones that were inaccurate high weight. You see, that's why you have a minus sign here. You flip it. And now this thing here, the weight of that hypothesis, is proportional to the edge. OK, look here. And here's the edge. That was the weighted edge of the hypothesis with respect to the previous distribution. The oracle had this distribution. And then this was the edge, according to which it picked the hypothesis. Hopefully, it gave you one of high edge. Now, if the edge is 0, then this should come out to be the weight of this hypothesis is 0. So it's useless. You see? You're going to use it in your final weighted combination. It doesn't help you. But if this is going to be large, this edge, then this goes up somehow. OK, I should put a plot in there. And you have to have some notion of goodness. Goodness, again, of the hypothesis provided by the oracle is high edge. And if you have the assumption, let's say, that your edge is always bigger than 1%, then that would be good, right? Questions? So this is the AdaBoost algorithm. Yes?
So those U's are for the T. So is that supposed to be U of T or U of T minus 1? Is it the accuracy in the new or the accuracy in the old?
It's on the teeth hypothesis. It's the accuracy of the teeth hypothesis. Yeah, there's always a problem in online learning when you switch from T to T minus 1. I always say what you get in the new trial is the t. So I got in the new trial the t hypothesis, so I index them with t, the previous one with t minus 1. But I'm certain that even in my slides I'm not perfectly consistent. Okay?
How do you know that such a hypothesis always exists?
You do not know. That's an assumption on your weak learner. Under the assumption, you know, in machine learning, we don't solve NP-hard problems. We just say, oh, this famous scientist couldn't do it, and these problems reduce to each other. That's the kind of thing. Under the assumption that you have a weak learner, which could provide you things with a small edge, then things will work. If you don't have that, it doesn't work. So we bypass this issue by saying under the assumption. OK, again, here's the protocol. Maintain a distribution. Get a weak hypothesis from the oracle. Update your distribution. Output the final convex combination. Here's a simple update. You take the new distribution is the old distribution times these factors. This factor is going to be bigger than 1 if you were inaccurate on this example, and less than 1 if you were accurate. So you put more weight on the hard examples. You got that? With multiplicative factors. That's the thing. And whenever you have multiplicative factors, which we'll see very soon, that means you regularize with relative entropies. OK? Yes?
Is there a particular reason for that function for the weights?
Yes. That comes from the regularization. And I will give you a big picture in the next class. Machine learning is actually a very simple thing. There's not that many different algorithms. There's just many different dress codes. They look different, and they're sold as being fancy. But there's 2 families of updates that we mostly work with. Relative entropy regularization, Euclidean distance squared regularization. Gaussian modeling, and then information theoretic. And I'll discuss that in the next hour. OK, so this is your basic protocol, right? And you update, you got a simple boosting algorithm. You have the little pictures that showed you how it worked. So AdaBoost is trivial to code, provided you have an oracle that gets you the good hypotheses. It is a fast update. The update is totally trivial. You just go once over the examples. Nothing to be done. Order n, where n is the number of examples. Fastest you can hope for. It has an iteration bound. You know, if you do a certain number of iterations, you know how to achieve a certain accuracy. I will discuss these bounds at a high level. I won't prove them to you. But I spent most of my time in this research on proving these kind of bounds. So it's a good initial boosting algorithm. If you have a new problem, you want to throw boosting at it and test whether it works. If AdaBoost somehow gets you good results, then you look up more sophisticated boosting algorithm. So AdaBoost is sort of your indicator to enter that kind of thing and check whether boosting does anything in that area. Right? Good. And I will teach you the fancy ones. That AdaBoost has too many iterations. Same hypothesis is going to be picked many times. Sometimes, right? And that's sort of, maybe you don't want that. And if your weak hypothesis cannot separate the data, then this thing cycles around and it kind of gets into a loop. And there's a certain reason for that. We understand all of that. But it's a good initial thing. So AdaBoost, Freudian Shapiro. So the questions that we're going to address is how to motivate these boosting updates. What are the underlying optimization problems? What is the regularization that motivates them? And how to get bounds on the number of iterations. So that's sort of the kind of questions that I'm interested in. Right? So this greedy scheme of adding one base learner, one feature at a time, how many features do you need before you're going to get accurate? So there's two basic applications of boosting. And I only focused on the first one. The first one says you build a strong classifier from the weak classifier. But there's a second one. The second one is you want to use boosting as a filter. So I want to determine the example that remain hard to classify after combining a set of base learners. So this was after the first hypothesis has been added. You say that means after the fourth hypothesis has been added, I already took 4 hypotheses into account. I intuitively sucked out all the information that was in those 4 hypotheses. I put the 4 hypotheses edge down, means I pulled out all the information, and then the remaining hardness, that's what my distribution provides. This is hard, this is hard, this is hard, this is hard. Do you remember there was a step function going across? And the step function was, these points were close to the boundary. So those are hard. So in some sense, boosting works as a filter. Very cute. Filter in the sense it identifies you what the hard examples are. So now, if you want to classify pictures as to whether there's a dog in there or not, you might want to look at those pictures again. Oh, was this really a dog? And maybe throw them out. So you can use boosting as a filter. And as a matter of fact, if you want to, you know, there's these things like pap smears. You want to figure out whether they mean cancer or not. Some of the best people who know, best agents who know how to do that are actually human agents. They look at the pap smears, doctors with experience. Well, if you provide the doctors with random pap smears, it's going to be extremely inefficient. First, you want to run a boosting algorithm. Right? You want to run a boosting algorithm. Do all the tricks you know from machine learning, and then determine what the hard pap smears are, these, and only give those to the human. You understand? So use it as a filter. So that's a very, very important use of boosting, which has not been used that much, but I have used it. It's very hard to write a theoretical paper on it because it's very practical. But sometimes practice is good. Yes?
If we were to say we were to detect outliers, use boosting for
yes.
outlier detection.
You can use outliers.
Yeah.
Detect outliers. That's another term, yes.
Yeah. So should we look at the final weights, like the last iteration weights?
Yes, at the weights at the end.
At the end.
Yes, yes. I have done this. I used to work in drug design, not good drugs, okay? So, you know, so we try to use boosting to do the following. So you have a bunch of artificial compounds that you combine together and to make possible agents that you could build. They are scaffold, and you add different radicals to your chemicals. And then that's a possible thing that you could build. And you already know, you have done certain measurements. Certain compounds didn't work. They were not active. Others were active. Those will become your weak learners. And then after a while, the boosting algorithm provided you a list of the examples and also a list of the features. You remember, I have 2 weights. So the list of the features tells you which combination got your high activity. And the list, the distribution on the examples, told you which ones were hard to classify as to active or non-active. So the chemist can look at both things proposed by the algorithm. If it looks at the final combination of features, that gives him an idea of what is a good linear combination of features that achieves high activity. If he looks or she looks at the weighting on the examples, it tells you which ones were hard to classify. Maybe those measurements, these activity measurements, you should redo. Maybe they were not right. Okay? So that's sort of an interactive thing, and that's a very important thing. Joachim Freund, at some point, had a project where he drove around with a car and he wanted to recognize bicycles. He was in Santa Cruz too long. There's a lot of bicycling. So recognize bicycles. So he used boosting as a filter to present the human with potential bicycles to classify. First, he did all machine learning. And then he had, on these crucial examples, the human had to look at, is it really a bicycle or not? Yeah? And then that sped up the filtering process. So in some sense, the human becomes just another weak learner. Right? Just throw them in also. It's another agent. Yes?
So does that mean it's been used in active learning to try and get users to label those examples? Or?
Sure. Yes, you could use it in active learning in some sense. Yes. There is interactive thing. Yes, you could use it in active learning. Pretty soon, you just have a lot of tricks, and it's hard to know what to prove about them, but they all work a little bit. Welcome to machine learning. Everything works a little bit. Nothing is a panacea. Right? And very often, different approaches arrive at the same accuracy. Like if you, what are some of the favorite algorithms? It's really frustrating. Let's say support vector machines, boosting. Okay, totally different family of algorithms, totally different approaches, because additive and multiplicative updates. I talk about that in a moment. You run them on your favorite problem, spam filters. Turns out the accuracy come out roughly the same. Very frustrating. But that happens very often. I don't know why. I know they do something totally different, but they somehow come up with the same accuracy. Maybe if you boost them, combine them, you get slightly better accuracy, but only slightly. Yes?
So the hard examples that you said, I mean, it seems that they are with respect to the weak learner itself.
Yes.
But for a max margin classifier, none of them would be a hard example, right? I mean,
so we will get an interpretation where we interpret the hard examples as being close to a margin. But it's not a geometric margin. It's totally confusing. When we only know how to think geometrically. We don't think information theoretically. I don't know why. So when we think about margin, we think about closeness and geometric margins. But this is information theoretic. And I will bring out the different margins. That's the third lecture. Okay? So let's do a little stretch, and then I'll talk about some other things, some big picture things. So you get 3 minutes or 5 minutes. It's okay?